We have the ability to determine the acceleration of an object while moving upward or downward on an elevator and while at rest. We can do this by weighing the object while moving upward and downward, and by finding its mass, and by using its weight to find the normal force and the force of gravity. This way, all the variables in our equation, f of n minus f of g equals mass times acceleration, will be accounted for except for acceleration, which is the variable that we'll be solving for.
We hypothesize that when you're at rest, the acceleration will be 0, and when you're going up, the acceleration will be positive, and when you're going down, the acceleration will be negative.
I'm Olivia.
I'm Thomas. Hi.
I'm Kyle.
And we're finding the acceleration of an elevator at rest, moving upward, and moving downward. We weighed Thomas in an elevator at rest, going upward, and going downward. Here, when he's at rest, we observed that his weight was 173.8 pounds. Now, on an elevator going upward, his weight was approximately 183 pounds. Finally, when weighing him going downward, his weight was approximately 167 pounds.
This is the person standing on the scale at rest, and the normal force is acting there, and the force of gravity is acting there. So the elevator is only going up and down, so we use the y-axis, and so we know f of n and f of g equals mass times acceleration. So then we go over here, and this is the formula we'll be using, and we know that this is in pounds, and we have to transfer it over to newtons, so we times it by 4.45. So then we put that in there, and we know that f of n equals f of g, so we can find f of g, or we can find the mass down here. So we put it in here, divide, find the mass, so that's there, and then we find, so yeah, like I said, we know that f of n equals f of g, so we put 773 in there, and we find acceleration, so the acceleration is 0. There's your answer at rest.
Okay, so now we're going to calculate the acceleration of the elevator while moving upward. Since we're only working with the y direction, so we're going to use the normal force, which is pointing upward, and the force of gravity, which is working downward, and those will equal mass times acceleration. So we're going to go back to the formula that we used for the first one. The normal force minus the force of gravity is equal to mass times acceleration. The normal force is what we see in the scale, so that was 183 pounds, so we need to convert that to newtons by multiplying it times 4.45. That'll give us 814 newtons, and so that'll go in for our normal force. Then we'll calculate the force of gravity by down here. We know the mass because that's the same as the first problem. And so we'll plug that in, which is 78.8, multiply that, and our force of gravity ends up being 772 newtons. So we'll plug that in, so 814 newtons minus 772 newtons is going to be equal to 78.8 times A. And once we subtract and divide, our acceleration ends up being 0.53 meters per second squared moving upward.
Now we will find the acceleration of the elevator moving in a downwards direction. Since we're talking about going up and down, we'll only use the y features of this formula. The formula we're using is force normal minus force of gravity equals mass times acceleration. To find the normal force, we do 167 pounds times 4.5 newtons, which gives us 743 newtons. And then we also need to find force of gravity. So we use force of gravity equals mass times acceleration. Plug 78.8 in for the mass, and you get 772 newtons. Then you do force normal minus force gravity equals mass times acceleration. So 743 minus 772 equals 78.8. times acceleration, which leads you to eventually get an acceleration of 0.36 meters per second squared in the downwards direction.
In conclusion, our acceleration at rest was 0 meters per second squared. Moving upward, our acceleration was 0.53 meters per second squared, and moving downward, our answer ended up being negative 0.36 meters per second squared, meaning that we were accelerating 0.36 meters per second squared in the downward direction. Based on our calculations, our hypothesis was correct in saying that our acceleration at rest is 0 and our acceleration moving upward is positive, while our acceleration moving downward is negative.